Good morning, all of you. Today, I am recording the lesson for the day 28. In this lesson, we are going to solve some problems on the moment of inertia. So, we'll first see the simple figures, standard figures for the MI, and then we will move to the composite areas. So, I am sharing the PPT for the day. Now, today's lesson is the moment of inertia calculations, and the previous classes we have defined the centroid, CG, moment of inertia, and theorems of moment of inertia. And also we had the problems on the centroid of simple standard figures and also the CG of the composite figures. And also we learned about the concept of MI and also theorems of MI. And also we learned about the formulas for the standard figures for MI. And in this class, we are going to cover the problems on the moment of inertia of standard areas and also the different sections. They are also termed as the composite sections, which are consisting of the different standard figures. Now, this is the first problem. Take down this problem. Find the moment of inertia of a rectangle shown in the figure about its central axis, that is IXX and IYY, and B about its base AB. Now take down this figure. So a rectangle is given with a base of 60 millimeters and height of 100 millimeters. Here the XX and YY are the central axis shown in the figure. Now we are supposed to find out the moment of inertia of this given rectangle about its central axis. That means here both axes we have to find out. That is IXX and IYY we have to find out, and also in the B, the MI about its base. So this is our problem. Now coming to the solution. We know that the moment of inertia. So first we will take up the A bit, that is the moment of inertia about the central axis, that is about IXX, XX and about YY. That way IXX and IYY we have to find out. And here the the centroid is located at the midpoint. Now we know the formula, the moment of inertia of the given rectangle about xx, ixx bar is equal to bd cube by 12. Here b is equal to 60, that is the width, and d is the depth is 100. So 60 into 100 cube by 12, it is equal to 5 into 10 power 6 mm to the power 4. Similarly, the moment of inertia about the y axis, I is equal to db cube by 12. Here the d is equal to 100, b is equal to 60. So 100 into 60 cube by 12. It is equal to 18 into 10 power 5 mm to the power 4. And coming to the moment of inertia about the base AB. So in this given figure, this is the base AB, and we need to find out the moment of inertia about its base AB. So for this, we also got to directly we got the direct formula, or we also can find the IAB value by using the IXX value and the area multiplied by the square of the distance between the two axes, because AB is one axis here and XX is one axis. This AB and XX are parallel to each other, and they are separated with a distance. That D is equal to 100 by 2, that is 50. So by using the parallel axis theorem also, we can able to know the moment of inertia about AB, that is IAB. So both the ways we will compare. Now firstly, by direct equation, the moment of inertia of the given rectangle about its base AB, IAB is equal to, what is the formula? That is equal to BD cube by 36. BD cube by 36. So here, by substituting the given values, we are getting the IAB is equal to 2 into 10 power 7 into mm to the power 4. This is the answer for the moment of inertia of the given rectangle about the base IAB by using the direct formula. Now we'll check once by using the parallel axis theorem also. So as for the parallel axis theorem, IAB is equal to IXX plus A into H square. Here IAB we know already directly given, that is equal to how much IAB is equal to, that IX is equal to 5 into 10 power 6. So that is IXX. And area you know, that is the width into height, that is 60 into 100. And into H is here the, what is the distance between the AB and XX, that is D by 2, that is equal to 100 by 2, that is 50. So the substituting the values, that is equal to IAB is equal to 5 into 10 power 6 plus 60 into 100 into 50 whole square. So it is also equal to 2 into 10 power 7. So the moment of inertia about the base AB is equal to 2 into 10 power 7 mm to the power 4, and in both the cases the same by using the direct formula or by using the parallel axis theorem. So it is giving the same value that we must note. So in this way, the parallel axis theorem can be used to find out the moment of inertia about any other parallel axis which is parallel to the central axis. Now we'll go to the next problem. Find the moment of inertia of a rectangle with 20 millimeters wide and 30 millimeters deep about an axis AB which is at a distance of 45 millimeters from its centroid. So for this very simple problem, so firstly for this problem, firstly we have to find out the moment of inertia about the x-axis, that is the central axis. Then we have to shift that moment of inertia to another parallel axis AB, which is at a distance of 45 millimeters from its central axis. So by this we can do it. So now we take this figure also. In this figure, the it is having a width of 20 millimeters and depth of 30 millimeters, and x-axis is the central axis which is passing through the centroid, that is the midpoint of the given rectangle, and there is another axis AB which is at a distance of 45 millimeters from the x-axis axis. Now we need to find out the moment of inertia of this rectangle about the given axis AB. So firstly the width is equal to 20 millimeters, that is B, and depth is equal to 30 millimeters, that is D, and area is equal to 20 into 30, it is equal to 600 square millimeters, and the distance between the centroid and the given axis AB, h is equal to 45 millimeters. So here we are assuming that the given axis is parallel to the x-axis. Let AB is the moment of inertia of the rectangle about AB, that is AB axis. Now we know that from the parallel axis theorem, the moment of inertia about the axis AB, IAB is equal to IG plus A into H square. Here IG is equal to the moment of inertia of the given rectangle about the x axis, and A is the area and H is the distance between the central axis and the given axis. So we know all the parameters and we can substitute the values here. So firstly we have one of the moment of inertia of the given rectangle about its central axis, that is ix, that is r, igx is equal to bdq by 12. So here b is equal to 20 and d is equal to 30. So bdq by 12, 20 into 30 q by 12, that is equal to 45,000 mm to the 4, and now iab is equal to this ig plus a into h square. So IAB is equal to 4500 into 20 into 30 into 45 square. So this is equal to 45,000 plus 600 into 45 square. So IAB is equal to 126 into 10 power 4 mm 4. So this is the required answer for the problem. Required answer for the given problem. So in this way we can find out the moment of inertia of the given rectangle about any required axis which is parallel to its centroidal axis. Now coming to the problem 3. So take down this problem. Find the moment of inertia of a rectangular lamina of 30 mm wide and 70 mm deep about its CG and the least radius of gyration. So this is the problem on a rectangle. Here he has given the width and depth of the given rectangle lamina, and asking us to find out the MI about the CG. CG nothing but the centroid. So sometimes they may mention CG or centroid, both are same. CG in case of the, generally we use in case of the solid figures, solid masses, and centroid is used to define the lamina. The centroid is for the areas of the lamina. So here also given the lamina. So if they ask CG or centroid, both are same, and we are supposed to find out the. And in this case, first we have to find out the both moment of inertia, that is Ixx and Iyy. The moment of inertia of the given rectangle about the x-axis, which is passing through the centroid, and also about the y-axis, which is passing through the centroid. That is Ixx and Iyy we have to find out separately. Then we need to find out the radius of gyration by formula, and whatever the value we are obtained out of these two, the least value we have to mention. That is called the least radius of gyration. Now coming to the solution part, width B is equal to 30 millimeters and depth D is equal to 70 millimeters. Now the area is equal to 30 into 70, it is equal to 2100 square millimeters. Now the moment of inertia about the x-axis, that is the Ixg generally it is equal to BD, the formula is BD cube by 12. So here the B 30 and D is 70, so 30 into 70 cube by 12, it is equal to 857500 mm4, and the moment of inertia about the y axis Iyy is equal to dB cube by 12. Here D is equal to depth and B is equal to width. So D is equal to 70 and B is equal to 30. So it is equal to 70 into 30 cube by 12. It is equal to 157500 mm4. Now generally the next step is to find out the least radius of gyration. So in both the cases we know that what is the equation for the radius of gyration. The radius of gyration is equal to under root of moment of inertia by area. So the we require what we will get the two radius of gyrations, but we need to find out only the least radius of gyration. So by seeing the Ixx value and Iy value, here the Ixx is having a more value, that is 857500, and Iyy is having the least value, that is equal to 157500. Therefore, the least gyration will be in case of the when we taken the moment of inertia about the y axis, that is Iyy. Therefore, the least radius of gyration k is equal to ky is equal to under root of Iyy by a. So that is equal to under root of 157500 by 2100. So that is equal to 8.66 millimeters. So this is the ky, that is the moment, the least radius of gyration. And if you find the kx also, you may get some higher value, but that is not required. We are supposed to mention the least radius of gyration. Therefore, the least value of radius of gyration is equal to 8.6 millimeters. That is the kyy is equal to 8.6 millimeters. So this is the answer. . Next, the other problem. Here, take down this problem. Find the moment of inertia of a rectangular lamina of 40 millimeters wide and 80 millimeters deep. Find the least radius of variation and modulus of section. Here also a rectangular lamina is given. We need to find out the MI and in both the cases, that is for XX and YY. Then we need to find out the least radius of gyration and also modulus of section. So first we write down the given data. Coming to the solution part, width given B is equal to 40 millimeters and depth of the lamina D is equal to 80 millimeters. Area A is equal to 40 into 80, that is equal to 3200 square millimeters. Now coming to the moment of inertia, that is the moment of inertia about the central axis and parallel to the x-axis, that is Ixx is equal to, we got the formula BDQ by 12. So here the B is equal to 40, D is equal to 80. So 40 into 80 cube by 12, it is equal to 1.707 into 10 power 6 mm4. And similarly, the Iyy, that is the moment of inertia about centroid and parallel to the y-axis. Iyy is equal to, the formula is dBq by 12. Here D is equal to 80 and B is equal to 40. So it is equal to 80 into 40 cube by 12. It is equal to 0.427 into 10 power 6 mm4. So these are the values for the Ixx and Iyy. Now, similar to the last problem, we need to find out the least radius of gyration. So if you see the Ixx and Iyy, generally the Iyy will be lower as compared to Ix value. So the radius of gyration will be lower. So if you use the Iyy in the formula, therefore the Kyy or Ky we have to find out. The Ky is equal to Iyy by A, that is equal to 0.427 10 power 6 by 3200. It is coming to be 11.55 millimeters. So this is the least radius of gyration of the section. Now we also know that the modulus of section. The modulus of section is denoted by the letter Z, and Z is equal to, this is equal to the Mi by Y. Here Mi means the moment of inertia and Y is equal to the distance of the centroid from the outermost edge. So in this case, if we take for example, you take any rectangle. So yeah, this is a rectangle. So this is a centroidal axis, and the distance between the centroidal axis and the outermost area. So this is what. So if this is 0 point, this is a d by 2. So this is d by 2 here to this side. So this is also 15. In this case, the total width is 30. So this part is 15 and this part is 15. So half of the width. So similarly, we should take here also. So here also the half of the depth. So d by 2. So if so the z is equal to Ix by d by 2. So it becomes bd by d into 2 by d. So that is also equal to the, if we simplify it, it is equal to bd square by 6. So that is the called the modulus of section z. So the modulus of section z is equal to bd square by 6. So b means 40, d means 80. So 40 into 80 square by 6, it is equal to 42,666.67 cubic millimeters. Then we are moving to the other problem. So here a composite figure is given. Here we need to find out the moment of inertia of the given composite figure, and for this we need to find out the what is called so this given is the I section. So this I section is nothing but it is composed of the three rectangles. The top flange, bottom flange, and in between the web. So the top flange and bottom flanges are the horizontal rectangles, and here the web is also a vertical one. And here the flanges are connected by means of the web. So it is a combination of the rectangles, and generally this high section is used in most of the engineering applications, because this high section will withstand the higher moment of inertia, higher bending moment. It will take more amount of roots as compared to the other sections. Therefore the high section is commonly used in the various engineering applications. Now take the problem. First you take this figure, then after taking the figure you take the problem. So here the as per the figure is concerned, the top flange and bottom flange both are same, having the same dimensions, that is 80 millimeters width and 20 millimeters depth, and the middle rectangle, the web, is having a thickness of 20 millimeters, or we can say it is a width, and height of how much, because it is 20 actually that 140 is up to only the bottom edge, so 100 by 20. Now this is the given rectangle. So now you take the problem, find the moment of inertia and radius of gyration about the central axis for the I section shown in the figure, for the I section shown in the figure. So this is the given I section. So first of all we will go to the solution part. Now first we will write down the solution for the moment of inertia, that is called MI solution. Now here first of all we need to find out the centroids, because the given I section is symmetrical about the y axis. So the centroid of the given I section will lie on the y axis, and we know that what is the x component. If we take the first of all we will define the reference axis. Here the bottom most line at the bottommost edge is the x axis, and the leftmost edge is the y-axis. So that is 0 point. Here the 0 point is shown here. This is the bottommost edge for the given section, and this is the leftmost edge. So this is the y-axis. So here the x and y-axis will intersect at this point. This is 0 point. That is the origin. The coordinate of 0, 0. And from here, if you see, the half of the AD is the total width of the flange. So the CG will be acting at a distance of 80 by 2. That is 40. The x coordinate is equal to 40 here. And we need to find out the y coordinate. Then after that, we have to find out the ixx and the iyy about the central axis. And then we need to find out the radius of gyration also. So here, now we have to split the given I section into the number of standard areas. If you see here, we got the 3 rectangles. So we have to divide the given I section into the 3 rectangles. So this is this bottom flange is called this one rectangle 1. So this web is called as the rectangle 2. So top flange is called a rectangle 3. Now, firstly, we have to find out the centroids. For that, we require the areas, then moment of inertia. So we know that the centroid can be found by using the table. So for this centroidal table, so we know that for the columns, the first one serial number, areas, here the centroids x coordinate, y coordinate, and the terms a into x and a into y. Then we'll find out the centroids here. Then after finding out the centroids, the difference point, that is hx1 and hy1, hx and hy. So the hx is nothing but the difference of the centroid of that particular rectangle from the centroid of the whole figure. That is x minus x1, or the difference between the x and x1. X means the coordinate of the x coordinate of the given figure. Y means the coordinate of the centroid of the given figure. Y1 means the y coordinate of the rectangle 1. X1 means the x coordinate of the rectangle 1, like that. So we need to find out the hx and hy, that is hx1, hy2, hy1, hx2, hy2, and hy3, hx3, and hy3, like this we have to find out. Now, firstly, if you know, write down the areas. Here, for the rectangle, it is equal to how much? So 80 into 20. So it is 1600. And the centroids, we know the by formula. So this is equal to x1 is equal to, so 40. That is 80 by 2, 40. The y1 is equal to how much? So 20 by 2. That is 10. And the term a into x1, a1 into x1, this is a1 into y2. Now the coming to the rectangle 2. Rectangle 2 is equal to, this is a web. And here the radius is equal to 20 by, it is 120. The given is 140, so it is 120 into 20 is equal to 2400. And the x coordinate is 40 because it is symmetrical about y-axis. So the x coordinate of all the rectangles will be same. So we should importantly note that whenever a given section is symmetrical about y-axis, here the centroid of that figure is that section is lying on the y-axis. So here the x distance is common. So here the x1, x2, x3 is common. So we directly can write down the x coordinate. But anyhow, we are finding to know that one. So here x1, x2, x3, both are, all three are same. That is 40 millimeters. And ultimately we get the x coordinate also at 40. Now the y term. So this is the y term, and here also for the rectangle 2. So here what is this is 20 we have to add plus 120 by 2. So 60 plus 20, that is 80. So this is the y term, and a into y, this is the value. Now coming to the rectangle 3, for the rectangle 3 also same. The area is equal to 80 into 2, 20, and here the x3 is same, that is 80 by 2, 40, and y coming to the y3 coordinate. So this is up to here. So 20 plus 120 plus this 20 by 2. So this 20 by 2 is 10. So 20 plus 120, 140 plus 10. So it is 150. The coordinate is, so y3 is equal to 150. And the term a into y is equal to this term. Now we have to find out the a1, the algebraic sum of the areas multiplied with the x coordinates, and the algebraic sum of the areas multiplied with the y. That is the sigma ai into xi, that is equal to 224,000, and algebraic sum of a into y, that is equal to 448,000. Now we know the value of centroid. The centroid is equal to sigma ai into xi by sigma ai. If you substitute the values, we will get the x coordinate is equal to 40 millimeters. And similarly, the y bar is equal to sigma ai into yi. So this is a value by the sigma ai. So if you substitute the values, you will get the y coordinate is equal to 80 millimeters. So these are the coordinates for the x bar and y bar, that is CG. Now this is the difference between the x coordinate and x1. So here for all these hx, because it is this given figure is symmetrical about the y-axis, the x coordinates for the individual figures and also that of the whole figure, that is individual rectangles, that is rectangle 1, 2, 3, and also the total section will be lying on the same line, that is the same central axis. Therefore, the difference between the x and either x1 or x2 or x3 will become 0. So this column will be 0. 40 minus 40 is equal to 0. Here, so this column minus this column. Here the for the y term, that is the hy1 is equal to here the 80 minus 10. So it is 70. And for the rectangle 2, it is 80 minus 80 is 0. And for the third one, so this is, so here this is 150 is here and 80. So 150 minus 80 is equal to 70. So 70, 0, 70. In this way, you have to find out the hx and also hy for all figures. Now we need to find out the moment of inertia about the individual figures, about its own central axis, and then we have to shift that moment of inertia to the central axis of the whole composite figure. First one, the further we take the section 1, the IGX1, that is the moment of inertia about its own central axis, that is B1 D1 cube by 12. By substituting the values, it is equal to 5.3 into 10 power 4, and IGY1, that is the moment of inertia about its y-axis, it is equal to D1 B1 cube by 12. So by substituting the values, we'll get the 8.3333.33. So this is 85.3 into 10 power 4. And we know the hy1, we got the 70 value. So area multiplied by the square of the distance, that is 69 into 70 square. So we got this 784 into 10 power 4. Now hx1 is equal to 0, therefore here the term is 0. Now for the section 2, similarly, so Igx2 is equal to B2 D2 cube by 12. So by substituting the values, so it is equal to 288.0 into 10 power 4, and Ig by 2 is equal to D2 B2 cube by 12. That is equal to 80,000. That is equal to 8 into 10 power 4. And here the H by 2 is equal to 0 and Hx2 also equal to 0. Therefore, the terms will be, the value of these terms will be 0. Now, for the section 3, the Igx3, that is nothing but the B3 D3 cube by 12. So substituting the values, it is equal to 5.3 into 10 power 4, and Ig by 3, that is equal to D3 B3 cube by 12. So it is equal to 85.33 into 10 power 4. Now the term H by 3, we got the value of 70. So area is, we got 1600. So 60 area into H by 3 whole square. So substituting the values, it is equal to 784 into 10 power 4. Whereas Hx3 is again 0. The term value is 0. Now coming to the, so this is a very important table from which we have to find out the what is called the moment of inertia. So here we got the, in this in the MI table we got the areas and Igx1 and A into H by 1, A into H by square, H by whole square, and then accordingly the Ixx1 and Ig1, Ig1 and A into H square, and accordingly I by 1. So firstly we know that these areas, and these are the terms, that is the values of the moment of inertia for the x-axis and also for the y-axis found by in the previous table that we have to copy. And these h by 1, h by values, h by 1, that is a into the term a into hy. So this is a1 into hy1, a2 into hy2, and a3 into hy3. We have to copy here, and this is the summation of this two terms, that is a and b. So these are the values. Now coming to the Ig y1, that is the moment of inertia about the y-axis from the table 80. So this is equal to 85.3 and 8 and 85.3 into 10 power 4, and we got the, here the hx term is 0 for all the figures, that is the rectangle 1, 2 and 3. So therefore, so these values are 0. This also we have to copy from the previous table, that is the central table. Then we have to find out the C plus D, C and D values. So adding the C plus D values here. So now here the total area, we know this value, and the moment of inertia of the total section is equal to Ix of the figure 1 and Ix of the figure 2 and Ix of the figure 3. If we add all these things, this is the total moment of inertia of the given composite section about the x axis, which is passing through its centroid. And here, if we add the moment of inertia of the given rectangles about the y-axis, then so we have to add all the things. So this is equivalent to 178.6 mm4. Now the next one is the moment of inertia of the given section about its centroidal x-axis is equal to 1866.6 into 10 power 4 mm4, and the moment of inertia of the total section about the centroidal axis is equal to 178.6 mm4. Now we also can find by from the formula of the perpendicular theorem of the MI, the perpendicular theorem axis of the moment of inertia, we know that the moment of inertia about the z-axis is equal to the moment of inertia about the x-axis plus the moment of inertia about the y-axis. So Izz is equal to Ixx plus Iyy. So by adding these two, then the Izz is equal to 2045.2 into 10 power 4. Like this, we can find for the Izz also. Now coming to the radius of gyration. So we know that the radius of gyration is equal to under root of I by A. So for the x's, we should take the Ixx, and for the yy, we should take the Iyy. So very simple. So that is the k xx is equal to under root of Ixy total area. That is 57.73 millimeters. And the radius of gyration about y-axis, that is ky is equal to under root of Iy by sigma a. It is equal to 17.85 millimeters, and the radius of gyration about the z-axis is equal to under root of, that is kz is equal to under root of Iz by sigma a. It is equal to 60.44 millimeters. So in this way, we have found the moment of inertia and the radius of gyration of the given figure about the x, y, and z axis. So this is the solution to our given problem. So in the summary point, coming to summary, in this lesson, we have found the moment of inertia of the standard figures like rectangles, and also complex figures about the central axis or about any axis or about the base by using the parallel axis theorem. And also we found the moment of inertia of the given figure about the z axis by using the perpendicular axis theorem, as Izz is equal to Ixx plus Iyy. Now Izz is, this is small quiz. So here the Izz is equal to, we know that very well that the answer is Ixx plus Iyy. That is the option A. Now the radius of gyration about the z axis, nothing but the Izz by sigma A. That is the first option. And there are the some of the questions that can appear in the examinations like this. Some of the, so this is the z section. Similarly, we can do it, and this is the I section. So like this, we can do it. So with this, we are closing the today's session. Thank you all.